Hi, welcome all to the online classes. I'm Mukesh Bhardwaj, going to represent a topic, deliver a topic on holography. In engineering physics, BTech first year, holography or photography. Holography and photography, the main difference between the holo and photo. Holo is a Greek word which means the uh, picture taken by the picture taken for the entire um, object or as a whole, holography. And photography is a two-dimensional photograph, and the holograph or holography is the three-dimensional view of any object, of any scenery, of any place. So, holography. Now, starting with the holography. What is holography? History of holography. Uh, Timeline. Basic terms and concepts in holography: interference, Fresnel Jones lens, visibility, influence of polarization, holographic recording and reconstruction, fundamental imaging techniques in holography, formation of holograms in journal, basic holographic equation, holography in everyday life, interesting articles to read on holography. So, up to till now, usual device for recording the image of an object, photos, sceneries, important events, etc., are on two-dimensional light-sensitive surface is photography. This recording is just opposite to the object or scene. Therefore, the recording on photographic plate is also called negative. The main defect of usual photography is that it records the way intensity varies across an object or scene. It gives no information about phase change or depth of the photograph is flat. Therefore, two-dimensional image of three-dimensional object or scene. Therefore, I mean to say that therefore two-dimensional image of three-dimensional object scene formed by a lens of constant focal length and seen only from one direction is recorded on photographic plate. In 1947, Gabor developed a device by which three-dimensional image of an object can be recorded and reconstructed by wavefront construction device with the help of highly coherent laser beam. This device is called holography. The word holo is taken from Greek language, which means total recording. In holography, both intensity and phase variation of light wave coming from different parts of the three-dimensional object are recorded on transparent photographic plate using interferometric technique. The recorded transparent photographic plate is called hologram. The holography produces images as true as the object itself, so the image can be seen from all angles. Gabor was the first to use this technique in electron microscope, but use of this technique in photography was hampered due to lack of availability of coherent light. After the discovery of high coherent laser light lathe and optanics in 1962, record the three-dimensional image of an object by holography. So, a method of obtaining three-dimensional photograph uh, images So these images are obtained without a lens. So the method is also called lensless photography. The records are called holograms, developed by British physicist Dennis Gabor in 1947. British physicist Dennis Gabor won the Nobel Prize in Physics in 1971. Making a hologram, a laser beam is just incident on a beam splitter, and this beam splitter uh, divert the beam in two direction, strike on the mirrors, then this beam is passed through the lenses, beam spreaders, and then it strike on the mirror through the one lens, and through the inner second lens is directly uh, incidence on the photographic film. So the interference pattern is showing on, and the object beam is showing. So this is the way we are going to make a hologram. Exposing a film to laser light, which is scattered by the object being holographed, and light coming directly from the laser. Uh, the film, the film simply records the interference pattern, which is the hologram. To view the image, the hologram is illuminated by light, which is diffracted by the interference pattern, thus reproducing the original surface pattern of the object in three dimensions. Production three attributes of light: intensity, color, direction. Not only the intensity distribution of reflected light is recorded, but also the phase distribution. Coherent reference beam interfere with the reflected waves. Viewed from different angles, the object is also seen from the different angles. Application: optical microscopy for organism. The most important application is interferometer. Three-dimensional pictures, the storage of digital data. A large number of pages can be recorded on one hologram. In interferometer, if one constructs two holograms of the same object on the same plate, and the object underwent a deformation between the two recordings, then upon reconstruction, the two holographic images phase difference in the certain parts of the two images will result, shows the deformation clearly. This method is extremely sensitive for deformation studies. So in construction of hologram, the light wave scattered from an object is superposed on a reference wave obtained from the same source of light, and the interference pattern is so formed. And the interference pattern is recorded on a transparent photographic plate. This interference pattern contains all the information about the intensity and the phase of the scattered waves. A transmitted signal through the fiber does not radiate. Further, the signal cannot be tapped from a fiber in an easy manner. Therefore, optical fiber communication provides 100% signal security. Small size and weight. Optical fibers cables are developed with small radii, and they are flexible, compact and lightweight. Fiber cables can be bent or twisted without damage. Further, the optical fiber cables are superior to the copper cables in terms of storage handling, installation, and transportation, maintaining comparable strength and durability. No physical electrical connections required between the sender and the receiver. And as fibers are very good dielectric, isolation coating is not required. Next, refraction and total internal reflection. So the phenomena of refraction and total internal reflection are shown in the slides. Angle of incidence less than a critical angle. In second diagram, angle of incidence equal to the critical angle. Angle of incidence is greater than a critical angle. So when the angle is incidence is less than critical angle, then the refraction takes place, and if it is less or it is greater than critical angle, then reflection takes place. One terminology, numerical aperture, is used in optical fiber. The numerical aperture of the fiber is closely related to the critical angle and is often used in the specification for optical fiber and the components that work within it. The numerical aperture is given by the formula Na is equals to N1 square minus N2 square to the whole root. The angle of acceptance is twice that given by the numerical aperture. Modes and materials. Since optical fiber is a waveguide that light can propagate in the number of modes, if a fiber is of large diameter, light entering at the different angles will excite different mode, while narrow fiber may only excite one mode. Multimode propagation will cause dispersion, which results in the spreading of pulses and limits the usable bandwidth. Single mode fiber has much less dispersion, but it is more expensive to produce. Its small size, together with the fact that its numerical aperture is small than that of multimode fiber, make it more difficult to couple to the light sources. So, according to the classification of optical fiber, there can be various classification of optical fiber depending on different parameters. We'll consider one by one. Classification of optical fiber depending on number of modes. There are two number of optical fibers depending upon the number of modes propagating into the fiber. Multimode step index fiber. Multimode step index fiber may be fabricated from either multi-component glass compounds or top silica. These fibers can have reasonably large core diameters and large numerical apertures to facilitate the efficient coupling to an coherent light source, such as LED. The performance characteristics of this fiber type may vary considerably depending on the material use, and the method of preparation. The doped silica fiber exhibits the best performance. A typical structure for a glass multimode step index fiber will show in the next slide. Now, almost the structure core diameter is 50 to 400 micrometer. Clad diameter is about 125 to 500 micrometer. Buffer jacket diameter is about 250 to 1000 micrometer. And the numerical aperture is 0.16 to 0.5. Now the performance characteristics: attenuation 2.6 to 50 dB per kilometer at wavelength of 0.85 micrometer, limited by absorptions or scattering. Now multimode graded index fiber. These multimode fibers which have graded index profile may also be fabricated using the multi-component glasses or doped silica. However, they tend to manufactured from materials with high parity than majority of multimode step index fiber in order to reduce fiber losses. The performance characteristics of a multimode graded index fiber one therefore generally better than those of multimode step index fibers due to index grading and lower attenuation. Multimode graded index fiber tend to have a smaller core diameter than multimode step index fiber. Although overall diameter include the buffer jacket is usually about the same, the typical structure is illustrated. That is, core diameter is 30 to 100 micrometer, clad diameter is 100 to 150 micrometer, and the attenuation is 2 to 10 dB per kilometer at the wavelength of 0.85 micrometer, with generally a scattering limit. Bandwidth 300 megahertz kilometer to 300 gigahertz kilometer. Application: these fibers are best suited for medium haul, medium to high bandwidth application using incoherent and coherent multimode source, LED and injection laser respectively. Now single mode fiber. Single mode fibers can have either a step index or gradient index profile. At present, commercially available single mode fiber are still usually step index. They are high quality fibers for wide band, long distance transmission, and are generally fabricated from doped silica in order to reduce attenuation. Now, single mode fiber has much less dispersion but is more expensive to produce. Its small size, together with the fact that the numerical aperture is smaller than that of multimode fiber, make it more difficult to couple to the light sources. Types of fiber, I had already given that brief review. Both types of fiber described earlier are known as step index fibers because the index of reflection changes radically between the core and cladding. Graded index fiber is a compromise multimode fiber, but the index of refraction gradually decreases away from the center of the core. Graded index fiber has less dispersion than multimode step index fiber. These are some pictorial representation of graded, multimode and step index fibers, in which their core diameter is varying, and I had discussed the advantages of each of the type of fiber. Now, dispersion in fiber optics results from the fact that in multimode propagation, the signal travels faster in some mode than it would in others. Single mode fibers are relatively free from dispersion except for intramodal dispersion. Graded index fiber reduce dispersion by taking advantage of higher order modes. One form of intramodal dispersion is called material dispersion because it depends upon the material of the core. Another form of dispersion is called waveguide dispersion. Dispersion increases with the bandwidth of the light source. Now, example of dispersion. If white light is fall on a prism, then a dispersion of white light gives the two light, violet and red. So the original signal and the dispersed signal is shown in the slide to the mode of figures. The fabrication processes the fabrication process of fiber optics are done by vapor phase oxidation technology. Today's fiber fabrication process include two major stages. The first stage produce a performa cylinder of silica composition 10 to 20 centimeter in diameter, about 50 to 100 centimeter long. This performer consists of a core surrounding by clad with a desired refractive index profile, a given attenuation, and the other characteristics. In other words, this is desired optical fiber but not on a much larger scale. Outside vapor phase deposition or chemical vapor phase deposition method, modified chemical vapor deposition MCVD method, uh, and one of the most important fiber optical fabrication process is plasma activated chemical vapor deposition PCVD, and the one is vapor axial deposition method. This vapor axial deposition method was developed in 1977 by Japanese scientists. Depositing the glass particles which were obtained from reaction among gases in heated zone occurs at the bottom end of the target or seed or rod that rotates the moves upward. This deposition form a porous perform, the upper end of which heated in the ring furnace to produce a glass performer. So losses in optical fiber result from attenuation in material itself and from scattering, which causes some light to strike the cladding at less than critical angle. Bending the optical fiber too sharply can also Bending the optical fiber too sharply can also causes losses by causing some of the light to meet the cladding at less than the critical angle. Losses vary greatly depending upon the type of fiber. Plastic fiber may have losses of several hundred decibel per kilometer. Graded index fiber, multimode glass fiber has loss of about 2 to 4 dB per kilometer. Single mode fiber has loss of 0.4 dB per kilometer or less. Types of losses: relative loss, wavelength. I had already discussed the banding of the fiber gives the losses. You see in the figure or in the slide, light escape through the core cladding interface if the critical angle changes. There are two basic type of fiber optical cable. The difference is whether the fiber is free to move inside a tube with a diameter much larger than the fiber or is inside a relatively tight fitting jacket. They are referred to as loss tube and tight buffer cables. Both methods of construction have disadvantages or advantages. Loss tube cables, all the stress of cable pulling is taken up by the cable strength members and the fiber is free to expand and contract with temperature. Tight buffer cables are cheaper and generally easier to use. Fiber optic cable construction. So, loss tube construction and tight tube buffer construction is shown. The innermost part is core, the yellow one is cladding, and the shaded gray is fiber buffer, air or gel, then tube. So this is loose tube construction. Now, tight buffer construction, core, cladding, fiber buffer, plastic buffer, Kevlar strength membrane or member, and the uppermost part is plastic jacket. Thank you. Now some questionnaires need to be discussed. I'll show you. Just wait a minute. Now some more slides which need to be discussed related to the fiber optic. Advantages of fiber. Fiber has three advantages compared with the metal wires: bandwidth, more data rate per second, longer distance, faster. Special applications like medical imaging and quantum key distributions are only possible with fiber because they are use light directly. These are the elements of fiber: data link, transmitter emit light pulses, LED or laser, connectors and cables passively carry the pulses, receiver detects the light pulses, transmitter, cable, receiver. Repeaters. For long link, repeaters are needed to compensate for signal loss. Fiber, repeat, fiber, repeat, fiber, repeat, fiber, repeat, and so on. Optical fiber, core, glass or plastic with higher index of refraction than cladding, carries the signal. Cladding, glass or plastic with lower index of refraction than the core. Buffer protects the fiber from damage and moisture. Jacket holds one or more fibers in a cable. Single mode fiber. Single mode fiber has core diameter of 8 to 9 microns, which only allows one light path or mode. Multimode step index fiber. Multimode fiber has core diameter of 50 or 62.5 microns, sometimes even larger. Allows several light paths or modes. This causes modal dispersion. Some modes take longer to pass through the fiber than others because they travel a longer distance. Multimode graded index fiber. The index of refraction gradually changes across the core. Mode that travel further also move faster. This reduces modal dispersion, so the bandwidth is greatly increased. Step index and gradient index fiber. Step index multimode was developed first, but rare today because it has a low bandwidth, 50 megahertz kilometer. It has been replaced by gradient index multimode with bandwidth up to 2 gigahertz. Plastic optical fiber, large core, 1 millimeter, step index multimode fiber, easy to cut and work with, but high attenuation. 1 dB per meter makes it useless for long distance. Sources and wavelengths. Multimode fiber is used with LED sources at wavelength of 850 and 300 nanometer for slower local area network. Laser at 850 and 1310 nanometer for networks running at gigabytes per second or more. Single mode fiber is used with laser source at 300 and 1550 and nanometer. Bandwidth is extremely high, around 100 terahertz per kilometer. Fiber optic specifications. These are some fiber optic specifications which we had discussed. That attenuation, loss of signal measured in decibels. Dispersion, blurring of signal affects bandwidth. Bandwidth, the number of bits per second that can be sent through the data link. And the most important, numerical aperture, measure the largest angle of light that can be accepted into the core. Attenuation and dispersion. Attenuation is expressed in decibels per kilometer. Dispersion, dispersion expressed in PS per. Measuring bandwidth. The bandwidth distance product in units of megahertz into kilometers shows how fast data can be sent through a cable. A common multimode fiber with bandwidth distance product of 500 megahertz can be carry a 500 megahertz signal for 1 kilometer or 1000 megahertz signal for 0.5 kilometer. If the core and cladding have almost the same index of refraction, the numerical aperture will be small. This means that light must be shooting right down the center of the fiber to stay in the core. Fiber types and typical specification. These are the fiber types: 50/125 microns, 51/125 microns, 62.215 microns, 100.11 microns, this. Core cladding ratio are like this. And these are some specification in regard of attenuation, bandwidth, applications, nodes. Popular fiber types. As there, popular fiber types. At first, there were only two common types of fiber: 62.5 micron multimode intended for LED and 100 Mbps network. There is a large installed base of 62.5 micron fiber, 8 micron single mode for long distance or high bandwidths requiring laser sources. Corning SMF28 fiber is the largest base of installed fiber in the world. Links. Gigabit Ethernet 62.5 micron multimode fiber did not have enough bandwidth for gigabit Ethernet. 1000 Mbps. LEDs cannot be used as source for gigabit Ethernet. They are too slow. So gigabit Ethernet use a new inexpensive sources, vertical cavity surface emitter lasers, multibode fiber designed for VCSELs. First came laser rated 50 micron multimode, bandwidth 500 MHz, kilometer 850 nanometer. Then come laser optimized 50 micron multimode, bandwidth 2000 MHz, kilometer at 850 nm. Distinctive aqua colored jacket. You can't make single mode and multimode fiber. You lose 20 dB at the junction. So we cannot mix the fibers of different mode. Mixing 50 micron and 62.5 micron multimode is not as bad, but you lose 3 dB, half the power, which is usually unacceptable. Fiber manufacture. Three manufacture or fabrication. One is modified chemical vapor deposition method. Second is outside vapor deposition method and vapor axial deposition method. Modified chemical vapor deposition method (MCVD). A hollow rotating glass tube is heated with a torch. Chemical inside the tube precipitate to form soot. Rod is collapsed to create a preform. Preform is stretched in drawing tower to form a single fiber up to 10 km long. Modified chemical vapor deposition. Tinted glass layer, soot deposition, glass, perform fabrication. Outside vapor deposition method, a mandrel is coated with porous perform in a furnace. Then mandrel is removed and the perform is collapsed in the process called sintering. Vapor axial deposition method, perform is fabricated continuously. When the perform is long enough, it goes directly to drawing tower. Drawing. The fiber is drawn from perform and then coated with protective coating. This is the phenomena. Index of refraction. Index of refraction. When light enters a dense medium like glass or water, it slows down. The index of refraction N is the ratio of the speed of light in vacuum to the speed of light in the medium. Water has index of refraction N equals to 1.3. Light takes 30% longer to travel through it. Fiber optic glass has N equals to 1.5. Light takes 50% longer to travel through it. Fiber applications. Step index multimode, large core size, no source power can be efficiently coupled to the fiber, high attenuation, low bandwidth, used in short, low speed data links, also useful in high radiation environments because it can be made with pure silica core. Next, graded index multimode, useful for premises networks like lanes, security systems, etc. 62.5 obliques 125 micron has been most widely used, works well with LEDs but cannot be used for gigabit Ethernet. 50 oblique 125 micron fiber and WOVSELS are used for faster networks. Single mode fiber, best for high speed and long distance, used by telephone companies and CATV. Fiber performance. So, that is all for today. In next lecture, we are going to start with attenuation or fiber performances. That is starting from the attenuation and the losses and the efficiency and all that. So thank you to all of you.